Welcome back. This is section 2.6, complex numbers. Hopefully you enjoyed the little introduction video. If you haven't watched that yet, please go back. The link is right above this video on eCampus. In this video, we're going to talk about how to understand and use the relationship between negative I and I and use it to write imaginary and complex numbers, and also perform operations with imaginary and complex numbers. So the first thing we need to remember is that an imaginary number is based on the idea that up until this point, we're not able to take the square root of negative numbers. So we came across the square root of a negative number, we said, okay, no real solution, and we wiped our hands of it and we walked away. Well, mathematicians had to come up with a way to deal with that. And the way they dealt with that was to create this concept of an imaginary number system, which as you saw in the other video, we're trying to move to calling them lateral numbers because imaginary numbers is kind of dismissive. So imaginary numbers, I is the square root of -1. And so everything we're going to talk about is based on this concept that we can take the square root of -1 and call it I. And so we can add them. So I plus I is 2I, and we can subtract them. So 5I minus 3I is 2I. And we can also multiply them together. So if I is the square root of -1, we can think of I squared as the square root of -1 squared. And so rather than taking the square root of -1, because we can't do that, we have to consider what a square does to a square root, and it undoes it. So we think of the square root of -1 squared as just -1. And so we can take the next step and say, well, what about I cubed? Well, I cubed is just I squared times I. And if I squared is -1, then that's -1 times I, which is just -I. And I to the fourth we can think of as I cubed times 1, or I, which is I cubed is -I times I, which would be -I squared, which again is the negative of I squared, which is -1, which is just 1. And so this pattern will continue. I to the fifth is just I to the fourth times I. I to the fourth we just discovered is 1 times I is just I. And so no matter what power we use, we will either get just I, or the square root of -1. I squared is -1. I cubed is -I. And I to the fourth is 1. And so I to the fifth is just I. I to the sixth will get -1. I to the seventh will get -I. I to the eighth will get 1. And so this pattern of either I, -1, -I, or 1 is the outcome of I to any power. So if, for example, I did I to the 10th, I can think of I to the 10th as I to the 4th times I to the 4th times I squared. By exponent rules, if you're multiplying them together, you add the exponents, so you can also rewrite them as split open exponents. And so I to the 4th is just 1. I to the 4th is just 1, and I squared is just -1. So 1 times 1 times -1 is just -1. So I to the 10th is -1. Okay, so simplifying the square root of -27, we can think of this as I, because the square root of -1 is I, the square root of 27, and then our reducing radicals rules apply. So if you're a little rusty with reducing radicals, you may want to go back and check out Khan Academy or come in for tutoring, so that way we catch you up to speed. So the square root of 27 we can think of as 9 times 3. So we can think of this as the square root of 9 times 3, and the square root of 9, of course, is 3. I square root of 3. Okay, so we're going to do something a little bit different in this video. After each example, I'm going to give you a you try, and I want you to go ahead and try this example using the same steps that we just did, and then we're going to talk about the answer in class. So pause the video, try this, and we'll be right back. Okay, so in example 2, we're going to simplify numbers that are either already in imaginary form, or you can rewrite the square root directly into imaginary form. So we can think of this as -5 times 3 times I times I. Multiplication is still commutative, which means you can multiply them in any order. Negative 5 times 3 is negative 15. I times I is I squared. Remember, we talked about I squared can be reduced to negative 1. And so negative 15 times negative 1 is just positive 15. Okay, go ahead and pause the video, try this, and go ahead and play when you're ready to come back. We'll talk about this answer back in class. Okay, so in example 3, we actually want to use the square root property. So in order to do that, we need to get x by itself. So we're going to start by subtracting 64 on both sides. So I squared equals negative 64. And then since we're solving for x, we need to undo the square. So we take the square root of both sides. And we end up with x equals the positive or negative square root of negative 64. So we can think of that as x equals the positive or negative I square root of 64. And the square root of 64 is 8. So we can rewrite it as x equals plus or minus 8i. Okay, take a moment to write this problem, try it, and go ahead and play the video when you're ready. Okay, so we've talked about imaginary numbers and how to multiply them together and reduce imaginary numbers that are raised to powers. But how do imaginary numbers interact with real numbers? And we created a complex number set. And what the complex numbers does is tell us that if we need to add a real part to an imaginary part, we can write it in the form a plus bi. Okay, so how do we do that? First, we need to recognize that the real part is separate from the imaginary part. So if, for example, we needed to find the values of x and y that make this statement true, we need the real parts to be equal to each other and the imaginary parts to be equal to each other. So we actually have two equations here. The 3x minus 5 is our real part because there's no I involved here, must be equal to 7, which is the real part of the right side of the equation. And then the imaginary part, which is the quantity y minus 3 times I, must be equal to the imaginary part on the right, or 6i. And now we have two separate equations, which are pretty simple to solve. If we add 5 to both sides here, we get 3x equals 12. We can divide both sides by 3, and x equals 4. We can do the same thing with the imaginary part because we can divide by I on both sides. I over I is still 1, so y minus 3 must equal 6. If we add 3 to both sides, then y must be equal to 9. And so y equal to 9 and x equal to 4 will make that statement true. Go ahead and pause the video, write this question down. Go ahead and try it. Remember to identify the real parts and the imaginary parts and set them equal to each other. And then we'll come back in class and talk about the answer. Okay, so how to add complex numbers. Remember, the associative property tells us that if we have two numbers being added together in parentheses and then a third number added later, we really don't need the parentheses. We can just think of it as a plus b plus c. And so that's in essence what's going to happen here. As long as this is addition, which if it's subtraction, remember we would need to distribute that -1, we can just rewrite it as simple addition. So this is really 5 minus 7i plus 2 plus 4i. Now, the commutative property tells us that as long as it's addition, so if we change this to a plus -7i, we can rewrite this so that we have the real parts together and the imaginary parts together. And so we can really write this as 5 plus 2 plus -7i plus 4. And so 5 plus 2 is 7. And -7i plus 4 is -3i. So the simpler form of that equation or expression would be 7 minus 3i. Okay, go ahead and take a moment, write this problem down, simplify it on your own, and we're going to talk about that answer in class. Okay, so when we subtract complex numbers, remember that we can think of subtraction as adding a negative. So really we could think of this as 4 minus 8i plus negative 1 times 3 minus 6i. And if that's the case, then we can just distribute this negative 1 into this quantity here, and then the associative rule applies. So we can think of it as 4 minus 8i minus 3, because negative 1 times 3 is negative 3. Negative 1 times negative 6i is plus 6i. And now we can rewrite the real parts together. So 4 minus 3. And we can rewrite the imaginary parts together, negative 8i plus 6i. So 4 minus 3 is 1. Negative 8i plus 6i is minus 2i. Okay, go ahead and write this in your notes, try this problem, and we will talk about it in class. Okay, to multiply complex numbers, we are going to use exactly the same procedure as we do when we distribute a binomial. So the first thing we're going to do is 1 times 2, so that's 2. And then 1 times negative 6 is negative 6i. And then 3i times 2 plus 6i, and 3i times negative 6 is negative 18i squared, because remember I times I is I squared. Okay, so now we have plus 6i minus 6i, so that's 0. This will become 0. So we have 2 minus 18. Well, I squared we know is negative 1. So negative 18 times negative 1, we really have 2 plus 18, which is 20. Okay, go ahead, pause the video, write this problem down, try it on your own, and we will talk about it in class. To divide complex numbers, remember an imaginary number is a square root, and we don't like to have square roots in the denominator, so we do want to rationalize this. In order to get the 5i out of the denominator, we recall that I squared is negative 1. So if we multiply by I in the denominator, that will give us an I squared in the denominator. But if we do that, we also need to multiply by I in the numerator, so that way we are multiplying by 1. Remember, I over I has a value of 1, and 1 times anything is just itself. So we're not changing the value of the fraction by multiplying by I over I. Okay, so now we have 4 plus I times I and 5i squared. Okay, so we need to distribute the I to the binomial in the numerator. So we're going to multiply 4 times I and I times I. So in the numerator we have 4i plus I squared, and in the denominator we have 5i squared. Okay, remember I squared is negative 1, so we can rewrite this as 4i plus negative 1 over 5 times negative 1. And simplifying this, we can look at this as negative 1 plus 4i over 5 times negative 1 is negative 5. But this isn't quite a complex number. We need to write it in the form a plus bi. So we can rewrite this as negative 1 over negative 5 plus 4i over negative 5. Well, negative 1 divided by negative 5 is just 1/5. And if the denominator is negative, that means the whole fraction is negative. So this is 4/5 I. And there is our complex number. Go ahead, copy this down, try this problem on your own. When you're ready, go ahead and play the video again. Okay, so to divide complex numbers, we need to remember a little bit about rationalizing square roots. And remember, to rationalize a square root was pretty easy if the square root was by itself in the denominator. But if the square root was like 1 plus the square root of 2, now we had to deal with the fact that we had basically a binomial in the denominator. And we used something called conjugates. And conjugates allow us to basically utilize the difference of squares idea. So if we have a plus b times a minus b, this is a conjugate because when we distribute out, we end up with a squared minus b squared. And that helps us get rid of the square roots. And if we remember, an imaginary number is basically the square root of negative number. So if we want to get rid of the square root, we want to force I to be squared. And so using the conjugate will help us do that. So if I multiply both the numerator and denominator by the conjugate of the denominator, so 3 minus 6i divided by 3 minus 6i, I'm multiplying by a value of 1 because this has a value of 1. It's the same thing over itself, and I'll get rid of the I in the denominator because I end up with 2i times 3 minus 6i over 3 plus 6i times 3 minus 6i. And to distribute this, I end up with 2i times 3 equals 6i, and 2i times negative 6i is negative 12i squared over 3 times 3 is 9. And then we look at 3 times negative 6i is negative 18i, plus 18i is going to be 0. And then 6i times negative 6i is negative 36i squared. And remember, I squared is negative 1, so we end up with 6i minus 12 times negative 1 over 9 minus 36 times negative 1. Well, to reduce that, we end up with 6i plus 12 over 9 plus 36. 9 plus 36 is 45. And we can rewrite this as 12 plus 6i so that it's in complex form. And in order to write it completely as a complex number, we need to split the fractions. So we end up with 12 over 45 plus 6i over 45. This fraction can be reduced by 3, so we end up with 4 over 15. And this fraction can also be divided by 3, so we end up with 2 and 15. So we end up with 4/15 plus 2i over 15. And this is the complex form, so a plus bi. You could also write it as 2 over 15 times I, but there's your complex number. Go ahead and write this in your notes, try it on your own, and we will talk about the answer in class. Okay, thank you so much for listening. If you want some more examples, go ahead and watch the more examples video below. Otherwise, go right ahead and complete the 2-6 complex numbers reflection. And up next is the quadratic formula and the discriminant.